same time, and they do this a lot in nuclear chemistry, you'll get this portion of the curves, this portion curves, and it straightens out. You can take the straight line here and get the rate of decay of one of the substances. Then when you subtract it off, you get another straight line, and you get the rate of decay of another substance. It's a much more complicated experiment. This is sort of an experiment you might do in a basic radiochemistry course. We're not going to do anything. I just pointed out you can work with that to pull out different rate constants for the decay of several mixtures of isotopes. Or not isotopes, radioactive nuclides. Okay, here are the different ways of determining the order of reaction. The method of initial rates, that's the only one you really have to worry about, because that's the one where I can put some data down on the problem and you can plot and divide and solve the simultaneous equations using the technique we described. So that's the one we'll use. Here's the graph method. That's the one I just demonstrated for you. And here's the half-life. And I'm not even got, there was an equation for calculating the half-life for first, second, at first order, zero order, and second order, but I didn't bother talking about that, and we're not going to do that either. But the half-life test is another way of doing it. Once you get the order, you substitute the data into the rate law to find the consistent value of K. Okay? And that's the other problem. We know the orders of each of the reactants, and we know the rate. We can solve for the rate constant. And the one thing, we did this in the, and somebody wrote me about it, and all I can tell you with that is, first part is to determine the orders, then to get the rate constant, you have to plug it into the equation like this. And what I can tell you is, if you don't round these things off, every single piece of data will give you exactly the same K. When I'm grading your lab reports on the kinetics experiment, that's one of the things I look for, because I plug all your data into a computer program. It solves and tells me what M, N, and O are, and it does not round off the data. The precision of the computer is about 15 or 16 digits, whichever operating system you're using, I guess. But anyhow, it has a lot of precision, or a lot of digits. Anyhow, the data isn't that good. But it has a lot of exact numbers in here, and that means this K comes out the same. When you start rounding these numbers off, you get whole numbers, or tenths, or hundredths. Then you start getting variations in the value of K for each of the trials that you use. And we saw when we tried to do the one on the online homework, I didn't come up with his answer. Oh, and by the way, I did go in and solve it with the exact numbers for the exponents, and it made it even worse. So it was even further away from that 790. And I don't know how he got 790, because eventually when I pushed the right buttons and used the parentheses, we all got 800 with the rounded numbers, and I said, well, maybe the problem is he used the exact numbers, and so I put the exact numbers in, then I got 827, which is even further away from the answer he had. So I don't know how he got 790, but that's the answer the program is looking for. So after you've done a few, if you haven't gotten enough, it's one bonus point. Don't worry about it. But did anybody try all those? Anybody get 5 right ones? Nobody? You got 5 right ones? Somebody got 5 right ones. There you go. So it does work eventually. And it's good practice. Okay, the next thing I want to talk a little bit about is the so-called Arrhenius equation for describing the reactions that occur. And basically, it goes through, and you can't see this, so I'll pull this down, because he has everything marked on here. I put these in the wrong order, but there's the Arrhenius equation, and this is the rate constant we were talking about in those rate equations, and it's some factor here that represents the number of collisions per second, the probability of a reaction occurring in each collision. So that's the A factor. This is the exponential function minus E sub A. That E sub A is called the energy of activation. R is the usual gas law constant consistent with the units of this, which will be in joules. This will be in joules. T is temperature in Kelvin. We're not going to do any calculations with it right now, but that is the Arrhenius equation for calculating the rate of reaction. The thing you might notice, as this number, the activation energy, gets bigger, what must happen to K? Gets smaller because of this negative sign here, right? Bigger activation energies, smaller rate constants at a given temperature. And notice, as you increase the temperature, what must happen to the rate constant? It'll increase. And also, the molecules are moving faster, there are more collisions. This number increases, and this factor will increase as you increase the temperature. And that's the integrated form. I'll come back to that in next, but I want to go back to this thing. So anyhow, this is called a reaction coordinate, or the progress of a reaction. This is the energy of the system. Here we start off with reactants. It goes up to the transition state. This energy difference right here is the activation energy from here to here. The higher this is, the higher the activation energy, and the smaller the rate constant, therefore the slower the reaction. It doesn't matter whether the products end up down here or up here. In other words, this one happens to be a lower energy state for the products than the reactants, so what type of reaction would you call that, going back to your thermochemistry? An exothermic reaction. You're giving off energy going from here to here. And it shows up with a negative number for the enthalpy of reaction.
For the formula we just looked at, it uses the term EA for both the forward and the reverse, but they're different numbers. So how would we know which one to use?
Well, we're always talking about the reaction as written, which means the forward reaction.
Okay.
But notice what this tells you also, if you're trying to go in the reverse direction, since it has a much higher activation energy, it's much less likely that you're going to have the reaction go back that way. But when we talk about rates, oops, wrong K, lowercase k, this is called, there, K sub F, forward, K sub R, reverse. These are the lowercase k's talking about rate constants. For this example here, you'll know that, oh, I know, K sub R is smaller than K sub F because it has a lower activation energy going in this direction than coming in the reverse direction. But when the system comes to equilibrium, these rates are occurring at the same rate. So if this number is smaller than this number, that means that this concentration of B is going to be bigger than the concentration of A when we get to equilibrium, which is our next topic we want to get to. Okay. So this is the reaction profile. Other books call it just following the progress of reaction or whatever. And you're looking at what happens as you progress in time. In other words, you start off here with reactants. They go through this transition state. Notice here they're colliding head-on. And you want to make the reaction, oh, I didn't write down the reaction, but it's N2 plus NO goes to NO2 and N2. So if they collide like this, you're going to get products. And here's the transition state where this oxygen that was originally attached to the N2O is now going to be partially attached to each of these. And now it can either break break apart here, and you go back to the original reactants, or it can break apart here and you go on to the products.
He has them written just underneath the
Pardon me?
consecutive. He has the formulas written just underneath reactants and
Yeah.
products.
Right over here.
Yeah.
Here's the products, and here's the reactant, N2O plus NO, gives you N2 plus NO2. You have to read the whole. I mean, he didn't write it as a separate equation anymore. He just said this equals this. Okay. So these are some of the considerations we talk about when we're talking about reaction profiles or the progress of a reaction. There are different ways of referring to it. And notice this can be a small thing. Well, let's go on to some other things that he does here. Okay, I guess he's talking. We're getting into mechanisms of reactions. When you get to organic chemistry, we'll talk a lot about mechanisms. But we talk about elementary processes. And one of my favorite reactions to talk about, and I'll say a lot about it when we get to equilibrium, is the reaction between hydrogen gas and iodine gas to make HI gas. And when I was doing my thesis preparation or whatever, a thing where you had to prepare a bunch of presentations for the faculty, one of the things I had was that reaction. I found about 900 papers about 45 years ago, and after reading half of them or 3/4, I didn't get to read all 900, but nobody seemed to really have definite proof that it was an elementary process. It's very hard to prove that a reaction is elementary is an elementary reaction. What it means is when you write the rate equation, the coefficient is the same as the coefficient of the molecule in the balanced. The exponent is the same as the coefficient in the balanced equation. So there are two types of elementary processes. Unimolecular just means one molecule sits there and it goes on to products by itself. Radioactive decay is unimolecular. Or bimolecular. That means two things collide and they go on to products. Now your book here says something about termolecular, three things collide, but things are colliding and bouncing apart so fast in any gas phase or solution phase that it's almost impossible to have a three-body collision. Termolecular means three things collide, because these two things have to collide and they're flying apart in millionths of a second, and the third one has to hit it right when they're together to make a three-body collision that would produce a reaction. So most books don't even mention it, but your book does mention it somewhere in the text. But the point is, for each of those, the exponents for concentration terms are the same as the stoichiometric factors, which means the coefficients of the balanced chemical equation. So